Welcome back. This time we'll do a paper 2 higher walkthrough of the Specimen series. If you haven't watched already, I'd recommend you also watch my paper 1 version, however it doesn't matter what order you do it in. And one very useful thing about exam questions is that it tests your ability to understand not only the content but how it's assessed. The best way to be prepared for the exam is to do the exam questions itself that you'll face. And that's the reason why everyone mentions about exam technique. And it's mind-blowing just how much content they can fit into 2 papers, even if they don't cover all of it. They cover a good chunk out of it, and you'll see throughout this whole Specimen series, you need to use quite a bit of knowledge here from the whole course. So I hope you find this walkthrough helpful. Now there'll be a link below in the description to also do this paper with me. I recommend you do it before I start the video or before I walk through it, and you do it in silence exam conditions. You'll then be able to watch how I go through the questions and note down any weaknesses. And if you need the formula sheet, well, here are the formulas that you need to know. Number 1. Tracy wants to find out what improvements to the youth club are wanted by the members of the club. She plans to give each member of the club a questionnaire. Here is part of the questionnaire. We have 5 questions and here they are. Part A asks us to explain why question 2 will not give reliable results. Before I resume this, I just want to point out that this is such a nice question for 4 marks in total, because you can, if you know the content, do this so fast, and it makes those harder questions later on, gives you a bit more time, and just reduces the stress a bit. Back to the question. Why question 2 will not give reliable results? Question 2 asks us to input our age. We have 10 to 12 years, 12 to 14 years, and 14 to 16 years. Take a minute and pause. Think about what is wrong with this. And there are 2 blaringly obvious issues with this. The first one, if you're a 12-year-old, do you select this box or do you select this box? Because by this question it indicates I need to select both of them. And the other one, although less obvious, though if you did spot it you could also put it, what if you're 9 years old or 8 years old or perhaps you're 17, even though youth clubs go up to typically 18. So it's missing out ages, so there's a lot of issues with this, and I'll go with that, but there's overlapping categories. Part B. Explain why question 3 is not a good question. Do you agree that the condition of the club needs improving? Now, it's not really obvious from the specific example. Try and think of it like this. If I approach you and ask this, Mars is a good chocolate bar, right? Well, you're going to feel inclined to say yes. You don't want to offend me, but let's be honest, if I asked you what your favourite chocolate bar is, it might or might not be Mars, and there's a high chance that it would not be Mars because there's so many other options available. So this is called a biased or leading question, because it's more of a psychological point in that you're pressured to say yes or no depending on how the question is worded. For example, my one was yes. If you go to someone and say, do you like the specific chocolate bar? Well, they might say yes in the moment just to not offend you, and that's a good way to think about it. As I previously mentioned, this is called a leading question. Part C. Explain why there might be a problem with the answers given to question 4. So let's look at question 4. How much time do you spend in the youth club? Well, I can put this. I can put 2, I can put 91, I can put, I don't know, I could put anything. Now, you can see what the problem is here. I could also put this. I could put 20. Now, it might be all nice and fine if a human is going through this, but well, let's say there's a massive club and you're going to put it through a computer software to automate this. Well, how is it going to process, I don't know, and 20 when it's trying to look at integer inputs? It doesn't have to be integer inputs, it could be the other way around, it could be that they only want letter inputs. So it's going to make the data hard to handle. And we actually call this an open-ended question, rather than these tick boxes, which are called closed questions. This is an example of an open question, meaning you can give multiple different answers, and there's basically endless possibilities. Part D. Explain why the answers given to question 5 may not be valid. Do you know someone who has caused damage in the youth club? Well, if someone you know, perhaps your friend, or perhaps it's someone you don't want to snitch on, well, you're probably going to say no. And another thing is that this isn't anonymized. It's quite clear that Tracy here is giving it to each member, and I'm going to assume physically. There's nothing about anonymity here, so we can't really assume that. And this is a sensitive question. And that's what the mark scheme wants you to understand, is that this is a sensitive question, so you're not going to really tell the truth in this specific, or you might not even answer it at all. There you go, awful spelling of questionnaire, but that's that. 2. Matthew recorded the scores in a memory test taken by some teenagers and their parents. The teenagers took the same test as their parents. The box plot shows information about the recorded test scores for the teenagers. The table gives information about the recorded test scores for the parents. On the grid above, draw a box plot for the recorded tests for the scores of the parents. So I don't even have to tell you what a box plot looks like, because they've kindly given us one here. As you can see, we've got the box at this part here, and then we've got these lines coming out of it, and perpendicular to that, we call these things here whiskers. So what does all of this represent? Well, they've actually kindly given us this table here, and it illustrates perfectly what a box plot contains. A box plot contains the least, the lower quartile, the median, the upper quartile, and the greatest. And here the context is around scores, and that's why they've labelled it scores. So here we've got our least, and I'll just label that L. This is our greatest value, I'll label that G. And then we have these 3 parallel lines, which are vertical. This one here, and this one here. Everything I shade from this region to this region, or in this side of the rectangle, is from what we call the lower quartile all the way to the median. The median, as you'll probably know, is the middle value. However, you might have not heard of lower quartile and the upper quartile. The upper quartile, and I'll abbreviate this one to UQ, upper quartile represents 3/4 of the data through, whereas the lower quartile represents 25% of the data through. And you'll obviously know that the median is the middle of the data set, it represents 50%. So the lower quartile is 25%, the median is 50%, and the upper quartile is 75%. You might want to take these into account. This is the 25% value of the data, this will be the 50% way of the data, and this is 75% of the way through the data. So we just have to plot this. So it's quite simple. You need a ruler. I recommend you do it in pencil, so you'll be able to trace over if you make any mistakes, because you don't get any second graphs in the exam, and if you mess it up, well, that's your mark gone. So what I'm going to do is I'm going to plot first the least scores. I'm going to make my way chronologically. You could, if you want to go through any of the other ones, for example the median or even the greatest score, it doesn't really matter as long as you just do it and just try to be as accurate as you can. Now I'll do the lower quartile. And I'll move to the median and the upper quartile. And then lastly, the greatest score is 39. And now I just need to connect these. I'll connect the top to make the box of the box plot. And then connect the whiskers to the actual box itself. And that is pretty much the diagram. Now, if you get all of those plotted, that's a free 2 marks. And at the end of the day, if you practice these, then it will be second nature. Part B tells us to compare the distributions. We need to give 3 comparisons and interpret one of them, and that's probably going to be context. So let's label the key thing. We're going to compare their distributions. Now that should instantly throw loads of words at you, and we'll go through those in a minute. And we have 3 comparisons, and of those we need to interpret one of those comparisons. Now, interpreting, instantly you think context. The 3 comparisons will be related to the distributions, and when you're thinking about that, you always go to the defaults. The defaults will always be median, and I'd always choose median. And then you can have one of IQR or the range. However, I always recommend going with the IQR. It's one of the safer bets, and it's just more statistically, it's a better measurement. So the mark scheme also tends to favor that. But you can use the range if you really want to. And then the other one, because distributions came to mind, was skew. So then let's look and actually go to the box plots. Now we can see the median at the teenagers part, if you read it off, is approximately, or it is at 31, which is here. And we can see that the median we've been given was 29. So we can say the median of the teenagers was greater than the median for the parents. And that's your first mark. The next one we're going to look at, now we've ticked off median, is IQR, and I'm not going to look at the range, I'm going to choose to do skew. Now we need to remember to interpret one of these, and I'm going to choose to do the IQR. You could well easily do the median. So for the IQR is another piece of information that you might not know, so I'll give it here, and the IQR is taken by getting the upper quartile and subtracting the lower quartile. So it basically finds the middle 50% of the data, everything within the box plot here. So we can see that the IQR for the teenagers, if we look at it, well, we can get this point to be 35, and this point here for the lower quartile, should probably say in this, is 24. So the lower quartile is 24 and the upper quartile is 35. What's the IQR for the teenagers? Well, we can just do 35, subtract 24, and we get 11. For the parents, well, we just got our ones here. We can use our upper quartile of 35, and we can also use our lower quartile of 21. 14. So the IQR for parents is greater than the IQR for the teenagers by our calculations. We're going to also write that. Now this is one of the safer bets to put your comparison or your interpretation in, so I'll put it here. And what can we gather from a higher IQR? If the IQR shows the middle 50% of your data, and IQR value for the parents is larger than the teenagers, that indicates that there is a larger difference in the middle 50% for the parents than the middle 50% of the data for the teens. So what we can say is that the teens tend to have more consistent memory scores on their tests. Okay, so we've done that. Now we're going to look at skew. So when you're looking at skew in a box plot, you need to identify if it's either positive, negative, or symmetric. Or let's just put none. They're both basically equivalent. So if we have a box like this, we need to identify what this looks like. And they're both not symmetrical because they have the split, which isn't exactly in half. And you can see that the left side tends to be more than the right side. If you can see it, it's just about, and you can count them by squares if you want, and you can see that the left side is indeed bigger than the right side. So I'd illustrate it something like this. Now, intuitively, you'd actually think that, wow, this is more towards the positive axis, so this will be some sort of positive skew. Well, again, I'm just going to flip it on its head, and this is going to be negative skew. It appears to be positive because the line that's dividing it is more in the positive region, which would associate with the right side. However, it's actually negative skew. And you can see both of these have negative skew. And that's just going to be my last point. So you get 1 mark from the top one, and then a mark from your second comparison, the context mark, which was your interpretation, and then your last distribution mark for the comparisons. Part C. The information for the teenagers is based on data collected from 56 teenagers. Estimate the number of these teenagers whose recorded test score was greater than 24. Okay, it wants to give us an estimate for the number which was greater than 24. So we're looking at the teenagers one here, the teenagers box plot. Greater than 24. Well, if that rings a bell, this was actually the lower quartile, because we earlier recognized that here. So if we're looking at an estimate for the number greater than 24, that's going to be everything to the right of that point. And we also saw that the lower quartile is 25% of the way through the data. If you imagine that, we have 25% of the data here, and then the rest of the data here. And the data needs to add up to 100%. So how much data is this here? Well, we can see that that is 75%. So we know that if we're looking for the estimate for the number of teenagers who was greater than 24 or greater than the lower quartile, we know that 75% of teenagers scored greater than 24. And now we can use that information and find that 56 out of the 56 teenagers, we had 3/4 or 0.75 of these scored greater than 24. And I'll just type this into the calculator. 42. Julie was investigating the relationship between the marks gained by students in their GCSE maths exam and then the marks gained by the same students in an A-level maths exam. Suggest a hypothesis Julie could use. Well, the same students take both of the exams, so I'm going to guess that in order to progress to A-level they must have done well. Therefore, students who score highly in GCSE maths should also score highly in A-level maths. Julie drew a scatter diagram using the marks gained in GCSE maths and the marks gained in A-level maths by each of the 12 students. For this scatter diagram, explain why GCSE maths is the explanatory variable. Now, there's 2 types of variables we have, is the response and the explanatory. Now, if we switch to science for a minute, you might know the response variable as the dependent variable. And you guessed it, explanatory is the independent variable. And the reason for this is that, well, you're going to take A-level maths after GCSE maths. So if you're taking GCSE maths before and you get your result for that, you can kind of see how you're going to do in A-level, as it's going to respond to basically how clever you were in GCSE. Not that that is really truly correlated, because you can't change in that 2-year period. But the idea is that you sit GCSEs first, and they're plotted on the x-axis, and the x-axis is where you put your independent variable every time. Part C. Explain, given a statistical reason, whether or not the scatter diagram supports your hypothesis in Part A. Well, our hypothesis in Part A was that if you do well in GCSE maths, you will do well in A-level maths. And what does a statistical reason mean? A statistical reason is any sort of measurement we can use on the graph. Now, there's a few I can think of: skew, gradient, correlation, and obviously the gradient is the correlation. And we can see that this one has a general positive correlation, is going upwards, like so. So it's a positive correlation. I need to just grab this out real quick. And because of that, well, we can see that our hypothesis is supported. Because as you can see, those with a lower mark in GCSE tended to get a lower mark in A-level maths, and the positive gradient or the positive correlation has shown that as you get a higher GCSE mark, you're more likely to get a better A-level mark. Using statistical software, Julia obtained the following information of her 12 students. The mean mark for the GCSE and A-levels are shown here, and the gradient of the line of best fit. What these give us is the double mean point, which is shown with x bar, y bar. As is, it's just the average of all the x values and the average of all the y values. We can clearly see that the x values here are our GCSE ones, and our y ones are your A-level maths. So we can kind of write this in the x bar, y bar format with the GCSE and A-level respectively. So that does give us 578 as our x value and 78 as our y value. And the idea of a line of best fit is that it goes through the double mean point and it also has the gradient. And the gradient is 0.7. Then the mark scheme does give you a leeway. It makes sure you need to make sure your gradient's between 0.6 and 0.8. But it's just good practice to nail it down first try and get 0.7 and not leave it a chance. So to do this, you're going to pick 2 points and you need to try and achieve a gradient of 0.7. Now we know that the gradient is equal to the change in y over the change in x. So it's going to make sense to try and plot our double mean point, 578 for the x and 78 for the y. I'll do that now. So now that I've done that here, we've got to plot a line through this part here with a gradient of 0.7. Now we've got to try and be as accurate as we can be, close to 0.7, and we can write 0.7 as any fraction equivalent to 7 over 10. This can be 14 over 20, it can be 70 over 100, it could be 35 over 50. For all we know, we could use any sort of scale. So I've decided that I'm going to choose 14 and 20. Now 14 over 20 is your y over x. So our x is actually 20 and our y is 14. This is some unorthodox method, but you can see that if you subtract the coordinates from each other, and please don't use this as an official method, and to be fair, this isn't a method mark, this is just how you're going to work it out. You can see that we get 558 and 64. And now when we join this up, if we actually find this point, 558, 64, now if we join these two together, and this is what we get. So we go along from 558 to 578, which is along 20, and we're going up from 64, sorry, and we're going all the way up to 78. And you can see the gradient is 14 over 20, or the equivalent of 0.7. So you've met the conditions that it goes through the double mean point, which is here, and then you've got a gradient of 0.7. Now that was a tough one, and they did give you a range of 0.6 to 0.8. That said, use some sort of method to make sure you're not very off, and don't do it by eye, because again, that could quite easily look as a gradient of just 1 rather than 0.7. Part E asks us to interpret the gradient of the line of best fit. Now the gradient of the line of best fit is 0.7. Now what does that exactly mean? If we go to a molecular level, for each mark we go and increase by 1, you can see a slight increase, but not exactly 1 for the A-level maths exam. If we extrapolate this a bit more, we can see that if we go across 10 marks, well, we get something roughly approximate to 7. So for every 10 we go up 7, and as you can see here, this one, as we went 20 along, we went 14 up. So you can see that for each additional GCSE mark we get 0.7 additional A-level marks. Julie wants to use the line of best fit to predict the A-level maths mark for a 13th student. For GCSE maths, this student gained a mark of 540. Explain whether or not it would be appropriate to use a line of best fit to make a prediction. Well, let's see. The 13th student got a mark of 540. 540 lies on this X line. Now, as you can see, that is outside the data range, and the data range, as we can see, was everything from this X point all the way to this X point, because the most outer values are this one and this one in terms of X. So if we're estimating for a value that's outside this data range, well, the first thing is it's not going to be reliable, and hence it's not going to be appropriate, and the reason we can give is that it's extrapolating or it's outside the data range. Number 4. For each of the 4 schoolhouses at his school, Lee is analysing the points scored in the sports competition. Using statistical software, he produced the 3 diagrams below. What we see here is some sort of line graph, a bar chart at the bottom, and we have a pie chart on the right here. A tells us to explain why diagram A is not appropriate for the data. Let's look at the data we've actually got. We've got some names, which are the house names, and we've probably got some sort of points system. So the points are here, and then the names are here for each respective graph. Now, why doesn't it work for graph A or diagram A? Diagram A you need to identify as a type of line graph. Now, from what I can recall, the only type of graphs that look like this is either a time series, a scatter diagram, or a line graph. And it can't even be a scatter diagram because it just doesn't work here. So what we need to identify is that the house names are not numerical data, so it can't be used. Lee wants to show clearly the proportion of the total points scored by each house. Explain which of B or C is the best diagram for Lee to use and why. Instantly, which one makes you think proportions? Well, it's obviously going to be the pie chart. The pie chart is literally a circle which represents the whole total, the whole, and from that you have your slices which represent the proportions. And the idea is that the pie chart shows a fraction of the total for each slice, therefore that's going to be the most appropriate one. And that's question 4 done. Question 5. Richard wants to find an estimate for the number of rabbits living in a section of woodland. He caught a sample of 25 rabbits, attached a tag to each rabbit, and then released the 25 rabbits back into the same section of woodland. 4 weeks later, Richard returned to the same section of woodland and caught a sample of 10 rabbits. 2 of these samples were tagged. Using the results, Richard estimated that there are 125 rabbits in this section of woodland. Show how Richard worked out his estimate of 125 rabbits. Now, there's a couple of words that instantly make me think about the topic, which, if you haven't noticed yet, is capture recapture. The first of which is tag and caught and things like this. Now, they typically use capture, caught, tag, and basically the format is always the same. It's always something like 1 week later or 4 weeks later, and they return and take another sample. And basically you should identify that this is capture recapture. Now, I've got a video on this and I've illustrated how to answer these type of questions. So if you're not familiar, I would recommend you watch that now. But if you are, then have a go at this and see if you get this. So the formula I use, and there are plenty of methods to go about, however I'm going to use the method I'm most comfortable with, is just to use the formula, which is uppercase M over uppercase N is equal to lowercase m over lowercase n. Now, in respect to each of the letters, I'm going to spend a bit of time labeling what they mean. The capital N here is the total. Here, that's what we're actually trying to estimate. We're trying to estimate the total population of whatever we're looking at. Uppercase M demonstrates the number in our original sample, or the first sample. Lowercase n, on the other hand, represents the number of our second sample. And lowercase m shows how much of that second sample were originally tagged. Now, this is all clutter, so I'm going to make them disappear. Now, edXL's actually been nice this time, and they've told us the number that we're trying to get to, 125. And you basically need to read between the lines and see what you want. An estimate of the 125 rabbits, well, that's got to be the total number of rabbits in the woodland. So, for that reason, we're going to try and find capital N. Now we need to identify the values which correspond to the letters of the formula. So, as we saw that capital M was the number of our first sample, let's find that value here. He caught a sample of 25 rabbits initially, and then he attached a tag to each rabbit. So capital M becomes 25. And we don't know N, and we're trying to find this, so we'll leave it as a variable. Now we need to try and find lowercase n. This is the number of the second sample. And we can see here, 4 weeks later, Richard returned to the same section, and he caught a second sample of 10 rabbits. See what I mean by reading between the lines, because it doesn't say second sample, but you need to interpret it as he returns. That means it's going to be the second sample. So our lowercase n is going to be 10. And then our lowercase m. Now lowercase m is the number in our second sample that was originally tagged, and that number here is 2. So now all we need to do is simply rearrange for n. Now if you're strong at your algebra skills, then you can do this quite easily. If you're not, watch my video on rearranging equations, which should help you in a way that you can feel comfortable with answering these type of questions. So I'm going to cross multiply, and if I multiply both sides by n, I get 25 equals 2n over 10. If I now multiply both sides by 10, I get 250 equals 2n. And then if I do this, and now I divide n by 2, you get n is equal to 125. And you can type this into your calculator to verify it. And that is part A done. By considering Richard's statistical method, discuss the reliability of his estimate. Well, let's actually take a look at what he's actually done. He's caught a sample of 25 rabbits with no mention of how he's done it, and 4 weeks later he returns. Now that's a key part there. And the tags, he uses tags, and this is a big one, and I highlight it in a video. This is just such a common pitfall of this method. The tags could fall off, and I'm going to use that. So we've seen that he comes back 4 weeks later. Well, in 4 weeks, a lot of rabbits can be born and a lot of rabbits can die. It's as simple as that. So that's going to skew his results either way, and he can't tell if they've died or if they've been born, so he can't really adjust his number for that. So what I'm going to say is that it's unreliable, which should be 1 mark, and then we're going to have to give 2 supporting reasons, as it's 3 marks. And basically what I'm going to say is that, well, the tags may have fallen off, and there's been a long time between the samples. Now, you could also put that it's a small sample, and that is true. He only caught 25 rabbits for the first one, and 10 rabbits for the second one, and somehow has come to a conclusion of 125. It's not statistically reliable in the sense that it's going to be 100% accurate, and a small sample size doesn't help. You could also say that the sample's not random, and I said this, he caught a sample of 25 rabbits with no specification of how he did it. And the rabbits may have not been mixed between the samples, and that is a key part of the method. You must mix the rabbits thoroughly with the existing population to ensure it's not biased. And yeah, that's basically it. For 5 marks, this question wasn't too bad. Question 6. Barbara found the following information about the average gross pay in euros for males and for females in 10 countries in 2010. So the countries and males and females and all that is listed here. Barbara investigates this information using a suitable graph. Using the information in the table and her graph, she reaches the following conclusion. There is strong evidence that for every €10,000 increase in gross pay for males, gross pay for females increases by €8,000. Okay, so that's just the question. So let's look at let's look at part A. Explain, given reasons, what Barbara is most likely to have done to reach these conclusions. We should consider which type of graph she will have used and why, how she will have used the graph and the information in this table. So the first thing we need to do is go back to the table. It says that using the information in the table in her graph, she reaches the conclusion, and she investigates this information using a suitable graph. So by using the word investigates and this information, it suggests that she's using the table in her graph, or the table formulates her graph, and then she's using the graph to actually investigate and analyze. So the question asks what type of graph she would have used and why. So what diagram can we actually use here? Well, the moment you realize that the countries are just points on the graph rather than having any relevance to this question, you understand that it becomes male versus female. And that is the whole point. She's concluding that males receive more pay than females. So there's no mention of countries, and we can just get that out of the way. And that leaves us with just two variables. Now, two variables means one thing, and that is bivariate data. The next thing we need to do to narrow it down is look at the type of data. Are we looking at continuous data or discrete? And you can see here that all the data is discrete. It's not continuous, so it couldn't be a time series or anything, even though there is no time value here. I'm just illustrating that. And now we've got two conditions, bivariate data and it's discrete. And what comes out to me is a scatter diagram. So what she could have used, or what type she would have used, is a scatter diagram. And the reason for this, because we need to give so, is that the data is bivariate. So now we've used this line here, or this bullet point, we need to focus on the next bullet point. How will she have used the graph and the information of the table? Well, let's focus on the information of the table first. We can kind of gather from this is that she's using her data in the table and, well, her hypothesis or a conclusion, and she's basically putting it into the graph, and we've already discussed that this is a scatter diagram. So when you're using a scatter diagram, and a quick illustration here, you plot your points, and what do you do with them? You join them, and what do you join them with? A line of best fit. Now, the line of best fit usually does two things. Well, it's got two components, and that is the gradient that you need to be mindful of, and also it needs to go through the double mean point, and we saw this in an earlier question in the video. And the double mean point is the average of all the x and y values. So it needs to go through that double mean point, and it has to have a gradient. So what's the gradient here? And you need to be careful not to mess it up or mix it up. And you need to be careful not to mix it up with this product moment correlation coefficient. Although it might seem similar, it's actually going to be that for every 10,000 increase in males pay, 8,000 increases in female pay. Now, before we move on to the gradient, we're going to have to identify which axis is for the males and which axis is for the females. So basically, the independent variable always goes on the x-axis, correct? So the independent variable is the one we're changing, or the one that we control. And the idea is that we're controlling what the pay was for the males, which was 10,000, and we were seeing what the response was in what the dependent variable was, and that was for females. So the females would go on the y-axis, and the males would go on the x-axis. And the idea is because we know what the pay for the males was, we're looking at how the females differs from that or responds to that. And therefore, for every 10,000 increase for males, we were going to have an 8,000 increase in females. And then you can just do your change in y, change in x, and you'd get 0.8 as your gradient. So what you need to identify for your next two marks is the double mean point and the gradient. And you need to be able to distinguish the gradient from the PMCC. The PMCC, however, we're going to use that after this. So let's just quickly write that down. And the gradient here tells us the relative rates of the change in gross pay. For example, how the change in females with respect to the change in men's pay. Okay, so now we've got 4 marks worth, and the question was 5 marks. So the idea is when you see a 5-mark question, you need to think about how it's asking you to lay out your work, and here it's giving you 2 major bullet points. You want to split your marks roughly half and half, and here was 3 marks for the latter. Now obviously it wasn't that easy to tell which one needed 2 marks and which one needed 3 marks, but you could kind of see the quantity of information they've given you. And to be honest, I just answered the question right there and then as fast as I can and as accurately as I can, and then see where the marks are coming from and see if I've missed anything from each of the bullet points. And the last one is the PMCC. We haven't spoken about that yet in detail. The PMCC basically shows how close the points are to a line. So this and this, they could have the same PMCC. Just because the gradient's different, the PMCC isn't to be confused with the gradient, which sometimes I feel it is. And the PMCC is a high value because the PMCC can be any value between -1 and 1. And because it's much more close to 1, because it's roughly 0.83 something, 832 I think, well, it's going to be quite strong correlation. And this strong correlation means her evidence is strong because as it goes up by that amount, it does go up by that X amount. And therefore, the evidence for her is strong. Explain why Barbara's conclusion, based on the data in the table, may be unreliable. And this is 1 mark. So I'm coming back to the question, and instantly you can see it's in 2010. Now, we're in 2026 at the time recording. This is 16 years ago. So one easy thing I can write, this is old data or it's out of date. Now, what could you also put? Well, you could put as a small sample, and we saw it here. There's roughly 10. Yeah, there's 10 countries, not that many countries, and for each of the countries, there's only 1 representative male and female, which is not accurate at all. And another point you could put is that it's secondary data, and that's true. It says here that she found the data. She didn't collect the data herself, she probably found it from an external source, maybe the internet. And it could be affected by varying exchange rates. To be fair, I wouldn't have thought that last point in the mark scheme. That's quite of a niche one. Anyways, that's question 6 complete. For question 7, the table gives information about the times taken in seconds by the athletes in the 5,000 meter Diamond League race held in Oslo in 2016. And we're given the table with our 20th percentile, our median, and our 80th percentile. The cumulative frequency graph shows information about times taken in seconds by the 18 athletes in the 5,000 meter Diamond League race held in Zurich in 2016 as well. And then there we go, we've got our cumulative frequency diagram. So, part A asks us to use statistical calculations to determine in which of the 2 races the times taken by the athletes were the least, and in which of the 2 races were the times taken by the athletes more consistent. You must explain how you reach your conclusions. Okay, looking at the first thing is the marks. The number of marks is 5. So we're going to have to make 5 important parts, not in 5 points necessarily. It says here using statistical calculations. Now that's an important thing because it means we're going to have to use some numbers somewhere. This and is important because it means you don't choose one of the points, you need to do both points. And the points are, we need to determine which of Oslo or Zurich, which I'll just refer to as the different races, which one was the least in general, and which one was more consistent. So that's basically our main points. We need to use statistical calculations to do those 2 points. So it might actually be useful for me to explain what this actually means. Percentiles. Now percentiles might look a bit daunting at first, but it basically holds the same principles as the lower quartile and the upper quartile, which we explored previously in the other question. We know that the lower quartile represents everything from 0, or it represents the 25th percent value of the data, and the upper quartile represents the 75th percent of the data. And for the same thing, the median is obviously the middle of the data, or 50% of the way. Now you can apply the same principle, and you see that the 20th percentile is 20% of the way through the data, and the 80th percentile, you guessed it, is going to be 80% of the way through the data. And that leads us to another thing, where we had the IQR, which was short for interquartile range. We now actually have something called the interpercentile range, which instead of using quartiles, which was the lower quartile, the upper quartile, and the median every 25% or quarterly, we're doing percentage. We're going to the 1%, and therefore it's called interpercentile range. So the interpercentile range is not specific like the interquartile range. The interquartile range is always the upper quartile minus the lower quartile, or 75 minus 25%. The nice thing about interpercentile range, well, it's usually typically around the 10 to 20 and 80 to 90 points. You can use any two percentages really, and here we've got our 80 and our 20 percentile. So it makes sense if you're going to compare this data, which is for Oslo 2016 to Zurich in 2016. If we're going to compare those two, then you might as well use the same format. And the format is, they've given for the first one is the median and the 20th and the 80th percentiles. Now with the median, we can just compare it just as we did with our box plot question, compare those two. And as you saw, we compared the IQR for the box plot questions. It's a bit similar here. We're just going to apply the same thing and find the interpercentile range this time and compare the two. Now, looking at cumulative frequency diagram, how do you find the median? Because first of all, you might as well look at that. We know that the median is half of n, or half of n plus 1 if you're looking at discrete, but since we're looking at a cumulative frequency, it's continuous data we're looking at, so we're going to do half of n. Now, if you zoom in closely, you can see that each box within here represents 0.5. You can see this goes up 10 squares, and it represents a distance of 5. So yeah, each box represents 0.5. And if you count downwards from 20 and 0.5, you kind of see that this is actually 18. The maximum value is 18. So we're going from 0 all the way up to 18. And halfway through that value is going to be 9, which is going to be roughly somewhere here. Now, if we do that, we draw a ruler at this point, and we basically mark off. So 9 can be found 2 squares below 10, as each one is an increment of 0.5, and you just join them together. Now we see where that hits. And we roughly get around, and you can see that the points here go up in 1, and this is kind of cutting it in half almost. So we can see that it's between 805, which is that bold point here, and then the one after that is 806. So we're looking at around 805.5 if we're being quite accurate. I'm pretty sure they'd allow you some leeway in the mark scheme if you're not too accurate, but you should be accurate. And you can see mine was slightly off here, the horizontal line, so if you went a bit more higher, it would hit dead on center between 805 and 806. So that's the median value for, I think that was Zurich, the diagram one. Yeah, so that's the mean one for Zurich. Now, mean, why have I put the mean? It's actually the median. So if we look at the median of Oslo, it was 794. So let's compare 794 to 805.5. So 794, which was for Oslo, versus median of 805.5. And this one was in Zurich. And now let's directly compare them. 794 is less than 805.5. Therefore, Oslo was quicker or quickest as median was lower. So we've looked at which one is the least. Now we need to look at the consistent part. Now the consistent part, if you go back to the earlier question for box plots, they're very similar. We looked at the median to compare, I think it was heights, the context was, if I'm not mistaken, and the consistency was measured with the IQR. The same applies here. We're looking at the interpercentile. We're looking, rather than the middle 50% of data, we're looking at the middle chunk of data, and we can't really tell what it is, other than the specific question, of course, where we're looking at the 80th minus the 20th. So we're looking at the middle 60% of the data here. But in general, we don't really know what it actually is. So the middle 60% of the data, just like the IQR, the idea is to give a measure of the spread of data and not affected by outliers too much. So to do the 80th and the 20th percentile, well, we're going to apply the same thing. If you don't know what I did for this one, I didn't really go through it in detail for the median, but we did half of 18, which gave us our 9. So half of 18 is equal to the 9th value on the y-axis, or your cumulative frequency for the median. Now if we look at our 20th percentile, now the 20th percentile is going to be, rather than half, it's going to be 1 over 5, or 0.2 multiplied by our total frequency, which is 18. And that gives us 3.6. Now we've got to find 3.6 on this again, so it's going to be below 5. We just have to count properly what that's actually going to be. Now it's a bit annoying because the scale is in 0.5. So 3.6 is actually going to be quite annoying to find. So this is going to be 4 2 squares belief, and then this is going to be 3.5. So we're going to go just slightly over. And doing that, okay. So yeah, I'm drawing the line slightly to the right too much, but you can see that it's kind of hitting 2 squares to the left of 800, and that is 798. So the value of the 20th percentile, that's y-axis by the way, is 798 from what we've seen. Now we'll just apply the same for the 80th percentile. The 80th percentile is going to be 80% of the way through the data, or 0.8 times 18, which gives us the 14.4 value on the y-axis. So to find this, we're going to just go to 14.4 on the y-axis. Again, because it's not a multiple of 0.5, it's going to be quite annoying rather than anything else. So we've got to just really aim for as accurate as we can. And that comes up at 814. So yeah, that one wasn't too bad because it lined quite nicely. Now the mark scheme should, and I'll double check it in a minute, they should give you some leeway on the values of your IPR values, which you're going to calculate now, and it'll be based off obviously the readings you get here. So if you're not 100% accurate, I wouldn't say don't worry, but hopefully you shouldn't worry too much in the exam. Just know that they do take into account human error. So to find the interpercentile range, we'll just do the value of the 80th, like the upper quartile essentially, minus the 20th, or the lower quartile in the other example. And then we'll just do 814 minus 798, type that into your calculator, and we get 16. So we'll just write that here. So the interpercentile range, and it'll be useful to mention that this one was for Zurich since we did the graph rather than the table. Was 16. It might be helpful now to look at the interpercentile range of the table, or Oslo. We have 808 as the 80th, 789. Now using the same method, the 80th minus the 20th, I'm just going to put them into the calculator. and I get 19. So I'm going to put that into the answer. So whereas for Oslo, now just as the IQR measured the middle 50% of the data, the interpercentile range works similarly to do a different proportion, but still the middle data, which should hopefully make it free from outliers. And the whole point of that is to measure consistency. So consistency, if you see a lower value, that's going to be the more consistent one. And here that was Zurich. To highlight where the marks came from, you would get 1 mark from actually finding the median, and then 1 mark from actually doing the comparison, so finding that Oslo was the quickest, and that would give you 2 marks. You then also get 2 marks from finding the interpercentile range for Zurich, and the interpercentile range for Oslo. That's another 2 marks, and then you get your last mark from obviously the context, stating that Zurich was more consistent. And by doing this, we've addressed the statistical calculations, the least values, and the most consistent values, and that's the 5 marks achieved. And yeah, you might think, well, it's not easy to think about it straight off the bat in the exam. You're just going to have to practice loads of questions and just brain dump. If you want to leave this for the last question, if you just want to go ahead, there's no shame in doing so, because sometimes you just need to leave the hardest questions till the end. I'd say this is what separates a grade 8 to a grade 9, because interpercentile range isn't typically taught that much. It's not emphasized on so much because it's just not covered that much in exam content. So if it comes up and you know this, well, you've got a heavy advantage over other students. The interquartile range of the race time in Zurich is 13 seconds. The greatest time taken by an athlete in the 5,000 meter race in Zurich is 840 seconds. Mo thinks that this time is an outlier. Determine whether or not Mo is correct. Now, there's 2 types of outliers you learn in statistics. The one is that we've actually used quite a bit, is 1 plus or minus 2 standard deviations. Now this is for sample data. But when we're talking in the context of IQRs and upper quartiles and lower quartiles, we have another formula for the outlier, which is the upper quartile plus 1.5 IQR and the lower quartile minus 1.5 IQR. If you want to visualize this, we have our lower quartile here, your upper quartile here, and then your IQRs are like this arrow and this arrow. Now, if your data falls outside this dotted line here and this dotted line, then you can say everything outside in this region and this region is safely an outlier because it's past the lower quartile minus 1.5 and upper quartile plus 1.5 of the IQR. So which one do we need to use? Well, he thinks the greatest time taken by an athlete is an outlier. Now, the question is that going to be the upper quartile or the lower quartile? 840 seconds on the graph. 840 is here. And if you trace it upwards, you can quite clearly see that this is at the top of the cumulative frequency graph. So by definition, it's not going to be in the lower quartile of the data, is it? It's going to be at the top of the data. Dare I say it, it's going to be near the greatest value of the data. So to do an outlier test, we're going to use the top equation here. We're going to use the upper quartile plus 1.5 of the IQR. Now, if we do this, we need to find the upper quartile. The upper quartile is the 75th percent of data. Go into your calculator and do 18 times 0.75, which is the equivalent of finding 75% way of the data, and we get 13.5. We need to find that here. Luckily, it fits to the scale. Right, so we get a value close to around 812.5-ish. I kind of drew the line off again because of the pen ink. It's kind of, you can see that it's not quite hitting the line, so it should be a bit more to the right. And looking at this value right now, it's bang on 812. So to compensate for that, I'd say it's 812.5, and that's what it says in the mark scheme. And also, just to verify, the mark scheme also accounts for what I just did there now, saying 812. It says anything which rounds to 800 and whatever the answer will be soon. The idea is they choose values, and if you're slightly off, let's say you chose 812 here instead of the value I'm going to do now, the calculation should get you close to the final answer, which means you should hopefully get the full marks. Anyways, so we need to look at the last one. We just need to substitute a value for the upper quartile, which we now know to be 812.5. We need to add 1.5 lots of the IQR. The IQR is going to be 812.5 minus something, but we don't know what that is yet because we haven't found the lower quartile. So let's find the lower quartile. The lower quartile is going to be 25% of the way through. So 25% of 18 is 4.5. So we're going to find 4.5, and let's do that quickly here. Again, it's around halfway through that little square, so it's going to be a point something. So looking at that just by eye is 799.5. I'm going to quickly type this into the calculator. 812.5 minus 799.5, and we get 13. So we need 1.5 lots of the IQR, which is 13. I'm going to type this into the calculator now, and you get 832. That's the final answer. Now, as I said, the mark scheme says anything which rounds to 832. So 832 is the limit for an outlier, and Mo thinks that 840 is an outlier. Well, is he correct? Well, yes he is, because 840 seconds must be greater than our bound of 832. If you think about it, the cutoff is here, and this is 832, and the data is here, 840. So it's outside the region for which it should not be an outlier. So it is an outlier, therefore Mo is correct. Just want to add now quickly that if you have any ideas or videos that you want me to make, be sure to leave them in the comments below. Owen collected data about the number of people per kilometre squared living in each of the 56 counties of England and Wales in 2015. Some information about Owen's data is shown in this incomplete table. So this is a grouped frequency table, as we have our class intervals here and our corresponding frequencies here. The number of counties that have at least 600 people per kilometre squared. Now we just need to use the number of people's column, which is this one here, and we need to find it where it's greater than or equal to 600 because of the at least 600. At least 600 means 600 inclusive. If it says more than 600, you typically assume this to be 601, 602, for example. That's just something useful for all exams. So that's these two columns here, because as you can see, this is 600 to 1000, and this is 1000 to 6000, and they are all greater than 600. So R plus S, well, we don't really know what R plus S is, but we're given another key piece of information here, 56 counties. Now, you should know that in a group frequency table, all of these values here should sum, and they should sum to give 56, because the total number is 56 counties. So we know all of this is equal to 56. So we can formulate an equation, and you could say that 15 plus 14 plus 14 plus R plus S equals 56. Since we're only interested in R and S, we'll basically just rearrange for R and S. And doing so, we get R and S, which is 13. And since R and S is greater than 600, this will just be our final answer. Part B. Use linear interpolation and the information in the table to find an estimate of the median number of people per kilometre squared. So the two key words, estimate and median. So we need to use linear interpolation. It's just a fancy term for finding the median. Now for continuous data, we typically use half of n. Now if you use half of n plus 1, it doesn't really matter. The mark scheme does account for that answer too. So half of n, what is n here? 56, because that's our total. So we can say that half of 56, which gives us 28. you want to find the 28th frequency or the 28th value. So the next step is looking at which row this is in. So if we look at the frequency here and we make our own cumulative frequency table, probably should be doing it on the right, but I'm going to have to do it on the left. So it's 15 when it's between this interval. When it's less than 400 as well, it goes up to 29. I'm just adding the 14, then I add this 14 and I get 30, 43, so 43. Now 28 is the value we're targeting, and 28 is clearly going to be within this row here because it's under 29. So we're trying to find the median, and we know based on the information that it's in this interval right here between 200 and 400. The question is, what value of x can we put down as our estimate? So we know that we're trying to get to the 28th value, and we know that this is the 200th to 400. Okay, so we also know that in this interval we have a total of 14. And at the start of 200, we basically have 15. And we get to 29. We want to get 28. So basically we need to represent it as a proportion. So to get from 15 to 28, we need to go 13 along. And so there we can do 13 out of the total of that interval, which is 14. And the class width is 200. Now an assumption of this, because it's an estimate, is that it's evenly spread throughout the whole interval. So we'll multiply it by 200. As you can see, 200 to 400 is a 200 gap. Now that's not all. Now we know how far into the interval we're actually going, if you visualize it. But where do we actually start? Well, we add it onto the 200. So if we kind of use it like so, we need to do 200 plus this. Now I'll type this into the calculator, and we end up with 386 to 3 significant figures. I mean, you can expand it first if you want more simply. And that's the final answer. Using the information in the table, explain how the mean of Owen's data would compare with the median of his data. Okay, now this is all about skew. You know that we can represent a group frequency table with a histogram. Now I'm going to do a rough plot of what this is. We have the table values of 14, 15, 14, 14, and then RNS, and we don't really know these values, but we know that it's combined 13. So the idea is basically a continuous version of a bar chart. We use it for continuous data rather than discrete. And you just look at the general shape. And the general shape goes towards the right. The tail goes to the right. And that means that outlier values are positive and they're pulling it upwards. So this is obviously positive skew. Now in positive skew, you should know that the mean is greater than the median. Now I'll write that down and explain it why. So obviously now's not the time to explain it all, but when you have a little diagram, the mode is basically the highest point you hit, and this is obviously symmetrical, so the mean and the median would be here. So a better example, going back to our positive skew, well, the mode will be here because this is the peak value, and looking at the mean is going to be pulled by these extreme values, like your outliers. So for example, if we had ages, so like let's say this is 150 years old, and let's say this was 150 years old, and this is pulling the mean age up. So the mean would be somewhere around here, and the median's always in between these two or equal to it for a symmetrical distribution. So we can say that the mean is going to be greater than the median. I'd recommend that you revise it in more detail if that short explanation didn't make too much sense. Part II. Explain whether the mean or the median is the most appropriate measure of central tendency for Owen's data. Just like the example I just spoke about. Now this example is about counties, but it would probably be better for me to just stick with the age example now. Now let's say 150 years old. If that's going to pull up the mean age, well, that's not really a good representation, is it? Now let's say you're trying to see the mean age of, I have no idea, but let's say you're trying to find the mean age of something, and having 150 years might not be what you want, as it pulls the mean age up. It's basically skewing the data. So the median is going to be the most appropriate here. Owen uses statistical software to draw a histogram to show the data he collected. Explain whether or not a histogram is appropriate. Well, we already said that earlier, that a histogram is appropriate because a bar chart is used for discrete data and a histogram is used for continuous data, so you can say yes. Now you'd also get a mark if you said that they're grouped data. Owen prints his histogram, but his page gets torn. Here is what remains. Work out the values of R and the value of S in the table. Okay, this looks harder than it actually is, so I'm going to go back to the actual table. Now, the parameters for R was the intervals of 600 and 1000. So we're looking at everything bound by this part here. So the idea is we want to get the remaining area. Now, this is frequency density and the number of people. Now, this brings us on to what the frequency density actually is, and the area in here is basically the frequency. So we can find the frequency, which is what we're trying to find here, the number of counties, by just using our formula. Now, the frequency is equal to the density multiplied by the class width. So, what is the actual class width here? The class width we've found is 600 to 1000. So if we write this out, 600 to 1000, no idea what I'm writing in red here. Then we can say that the class width is 400. And that makes sense. And you can kind of see that it's going to be a rectangle, because if you cut this, if you finish this off, you get this. So we're trying to find the area of this entire shape. So we know that this is 400. So now it makes sense to find this side here. And this side is just the frequency density. Now this requires you to read off what the corresponding y-axis or the y value is. So you can see the increments here. Well, it's 0.005 for 5 squares. So one individual square would be 0.0001, and half a square would be 0.0015. I know, that's quite crazy. So 0.001, let's use that as the benchmark. We need to go above 2 squares, and then another half square. As you can see, this is quite intricate, but it's half a square. So we go half a square above that. So we need to do 0.01 plus 2 squares plus half a square, so just 0.0015. I've just looked back and I made a crucial error. Half a square is actually 0.0005. So these needs to be fixed there. I'll concede that. Sorry for the mistake. So doing that, you put this into the calculator and we actually get 0.0125. So now we know that. We know what the frequency density is, we know what the class width is. Now we can just use the formula, or you can just find out that is the area. But the formula is something useful to know for statistics, at least, because you might need to find the other variable in a different question. So we'll just do 0.0125 multiplied by 400, type it into the calculator, and we get R is equal to 5. Now you might think, how on earth am I going to use that to find S, which is presumably this part of the histogram? Well, now you can just use some common sense. If all of this adds up to 56, and now we know that this is actually 5, well, now you can just put that back into the formula. You can see that R plus S is going to equal to 13, so S must be 8. And you can show that in the calculator, or you could just write it in. It's not much workings you need for this one. And that is question 8 done. Question 9. Okay, we're moving to absolute and relative risk. Now, as statistics does have its perks, this is one of the topics that has historically been my weakness, and I don't particularly like it because it's just hard to get your mind around. That being said, I'm going to try my best. The ambulance service has a target of responding to 75% of life-threatening calls in 8 minutes or less. The table shows actual response rates for 2 locations in the UK in 2014. For a life-threatening call made in 2014, write down the absolute risk that an ambulance takes more than 8 minutes to respond in Littlehampton. Highlight the information we've been given. Littlehampton, and we need to find the probability or the risk it takes more than 8 minutes. So it is a percentage, so it's a probability in that sense. So this is for 8 minutes or less. So if 75% are answered in 8 minutes or less, then 25% are done in 8 minutes or more. So 25% are done in 8 minutes or more. Now write down the absolute risk. The absolute risk means that you're just looking at that in general. You're not looking at it in comparison to another variable or another location. So you'll just be 0.25. For part II, we need to work out the relative risk that an ambulance takes more than 8 minutes to respond in York compared with the target. Now, we need to bear in mind that the target for the actual national was 75%, and Littlehampton actually met that, so that's quite a interesting thing to note. So the relative risk has a formula. It's the risk of group A over the risk of group B. Now the risk of the order you do it in does make sense, because you need to find the relative risk of York compared to the target, and the target is 75%, as we've seen here. So the relative risk of York compared to the target would be finding the risk of York itself, and the risk of taking more than 8 minutes, we've already clarified it, would be 100 minus 93, which is equal to 77%, sorry. So we know that it's going to be 7%. Now the national average was 75%, and coincidentally Littlehampton had 75% as well. So we already know that it's going to be 25% of the time it's going to take longer than 8 minutes. So if 25% of the time it takes longer than 8 minutes, and York compared to that only takes 7%, so we can say 7 over 25%, which is just 7 over 25, and that's your relative risk. And the idea is, if you think about it as it is a decimal, it is 0.28, if I'm not mistaken. So if it's 0.28, it's saying the risk of an ambulance being later than 8 minutes in York compared to the country is 0.28. Now if the relative risk was equal to 1, you'd say that they're roughly the same, like the risk is going to be the same wherever you are in the country. If it's greater than 1, then the risk in being in York of having a late ambulance is going to be higher, but because you're looking at York compared to the country and it's less than 1, it's going to be a lower risk, which makes sense because York's quite good. Look, they've got a 93% response rate. So that's the answer, 7 over 25. So you probably see what I mean by relative risk being mined. It's a concept that you need to properly understand, and I'm a bit rusty and I have not done it for a year, let alone when I was revising it. I always found it a bit of a daunting topic. However, don't let that deter you from doing it, because it could come up and you should know all the content regardless of how difficult you find it. So yeah. Number 10. Adila and Brandon both travel to work each day. Information about their past journey times in minutes is given in the table. On Monday, they each took 60 minutes to travel to work. Calculate the standardized scores for the 2 journey times on Monday. Before we start this question, I just want to point out that GCSEs always seem tedious and feel like they have no value to it, but this is actually a real life application. Standardized scores, for some exam boards at least, are used to calculate if you miss a paper, for example. It's used to estimate what score you would have got, and they apply that to your real grade. I thought I'd just point it out before we start. So back to the question. So we're given 2 people, their mean time and their standard deviations for their previous journeys, and we need to calculate the standardized scores. And I say just move straight to the formula because it will help you understand what the standardized score actually is. So, the standardized score is equal to the value subtract the mean divided by the standard deviation. The idea is that you basically, it's a bit like standard deviation if you think about it. It's a similar measure, and the idea is you can compare the two values, or you can compare two data sets together because of this. So we need to actually calculate the standardized scores for each of the two journey times. So let's do it for Adila first. I'll double check, but I think you need to remember this formula. I don't think it's given in the formula book or anywhere else. So we need to do the value, and the value for both of them was 60. So we need to do 60 minus the mean, and the mean for Adila's was 75, and then divided by the standard deviation, and the deviation was 10. Doing this, we type it into the calculator, and we get negative 1.5. Now we'll do the same thing here for Brandon. So Brandon, again, we take the value, which is given to be 60 again. We subtract his mean, which is 65, and divide it by his standard deviation, 4. This gives us negative 1.25. And there's our 3 marks. So as long as you just knew the formula, from there it's really straightforward. Part B. Using your answers to Part A, explain which of Adila and Brandon had the better journey time on Monday. Now for this part you need to be careful. If anyone tells you to remember, oh, a higher standardized score means X or Y, no, you need to look at it in context. Because if I was to say that the mean was for the marks instead of journey times, then surely you'd want a higher mark for your exam. But in the context of minutes and your journey time, you want your journey time to be as low as possible. So who had the journey time as low as possible? And now I can actually explain what standardized scores actually are. It basically shows your relative standing of a specific value with respect to the dataset. And Adila had a negative 1.5 and Brandon a negative 1.25. A standardized score of 0 suggests that you're basically at the mean, or the expected, you're basically at where everyone else or your previous datasets mean. And that makes sense. You'd have 0 on the numerator because the value in the mean is the same. So the idea is the lowest standardized score here in this context will be the better one, because it suggests that the journey time in minutes will be the lowest for Monday. So we'll say that Adila, because she had a standardized score of negative 1.5, and therefore we'll say she had the better journey. Part C. Explain why standardized scores are appropriate to use in this context. Well, the idea is the formula basically shows the values and the mean and the standard deviations. So all 3 components are satisfied there. But what the main key component is that we can see that the means and the standard deviations are different. Now this tells us the distribution of the data, if we were to sketch it over a relevant diagram, would be different shapes. Now when I say the phrase, I need to hold you to a standard, that instantly should make you think about consistency. If you hold something to a standard, therefore like your chocolate bar or your favorite ice cream, you're always going to hold it to a specific standard, i.e. make it consistent. So in order to compare the values, they need to be consistent, and so standardized scores allows us to do this, and because they are basically, the clues in the name, standardized. Question 11 says that the time series graph shows information about the total amount of money in millions of pounds spent in the UK by overseas tourists for each quarter between 2011 and 2013. Divya says that the time series graph shows seasonal variation. Explain whether or not she is correct. So let's highlight the keywords we have here. Explain and seasonal variation. Now we need to actually know what these two mean. Explain, it just means give a reason. So we need to say yes or no to whether it has got seasonal variation and give a reason for that. So seasonal variation. Well, what is seasonal variation? If you think about it out of context for statistics for just a minute, well, if you think about seasonal variation, let's look at it in respect to ice creams. For ice creams, you'll see that there's high demand in the summer when it's nice and hot, But in the winter, you're not going to be wanting an ice cream, at least the general public anyways. So that's seasonal variation. So what you'd expect if you saw the quantity, for example, if that was on the y-axis instead, you'd see high peaks at the quarter 2, which is the summer quarter, because quarter 3 and 4 are autumn and winter, and that basically indicates seasonal variation, because you're seeing a pattern. Every summer you see high demand for ice creams compared to the other seasons. So the point is, are we seeing seasonal variation? At each of quarter 1 for 2011, 2012 and 2013, the corresponding values are plotted here, here and here. Now, if you can't divide the years up, so you can say that the new year starts at quarter 1, so just about here, and then also just about here, where you can see that this is consistently the lower value. For quarter 1 of 2011, out of all the quarters, it's the lowest value. For 2012 and 2013, the same applies. So the idea is this is a pattern, it's always the lowest value. And we can say the same for quarter 3, as we can just spot that that is the peak. And you can see that this value, this value, and this value are all for quarter 3. So it doesn't have seasonal variation. We can say yes, because it follows a regular pattern. And it's repeated at the same time every year for 2011 through to 2013. You're also welcome to use the first quarter as an example. Part B. Divya considers finding 3-point, 4-point, or 5-point moving averages for the data in the time series graph. Explain which of these moving averages is the most appropriate to find. I'm going to rephrase the question. Is Divya wants to find a moving point average. What is an appropriate number? And so just answering this question, you'd instantly say 4, or I'd hope you'd say 4 anyways, because in a year you have your summer, autumn, winter and spring. You have your 4 seasons, and naturally you also have 4 quarters. So you can see that we have 4 quarters here. So it makes sense that you want to use a 4-point moving average. If you use a 3-point moving average, well, sure, you're using the quarters 1, 2 and 3, but what about number 4? So we can say that it's indeed the 4-point, and this is because of its 4 quarters. Divya wants to calculate an estimate for the spending in the UK by overseas tourists in the quarter 1 of 2014. Part C. Describe how Divya can use moving averages, the mean seasonal effect, and the time series graph to do this, and just note that it's a 5 marker. I'm going to pick out the keywords here, and here it is just calculating an estimate, and we're going to look at quarter 1 and then 2014, and the keyword here is describe. Now you might get carried away because you might have seen me answer other 5 markers using actual data values, but the keyword here is to describe. You're not actually doing the process, so you don't need to show any specific values, for example, actually calculating what you're going to describe. It's a bit like saying, well, this is completely irrelevant, find the mean of x and y, and then you need to plot them. Now, instead of me actually saying, let's do x plus y divided by 2, we're just going to say find the mean of x and y. We don't really need to do much more than actually just say what you see, and that's what describe means. So before we actually do the question, I'm just going to show you or give a brief explanation of what the actual process is. So the whole point of time series and looking at seasonal variation is that we plot moving averages, and the whole point of moving averages is it tries to smooth fluctuations that is shown by seasonal variation. As we've seen here, we have peaks and troughs because of seasonal variation, for example, our ice cream example. So the idea is that we plot the average of these 4 points here that I've circled, and then these 4 points here, and so on, and keep on going up one more as we keep doing our 4-point averages. And what you should find is if you plot it in the midpoint, you get something that looks a bit like this. You get something a bit like this. I just need to know what's the actual scale, so no idea if this is actually right, but the whole point is I'm trying to illustrate, and you get something, and then you want to draw it with a line of best fit, or a trend line, what it's actually called. Now I probably should move that up a bit, like so. And basically, you're going to use this trend line and you're going to see how much the deviation is from the actual values. And now you know a line of best fit tends to estimate values, and the same as here. You have your trend line and then you have your values and you have the distance between these values. You want to find the average distance between the values. And now if you find the average distance between the values and you extend this line, so let's keep extending it, so perhaps something like so, like this. And now we've got our average. We can basically add on the average, whether it's positive or negative, to here, and we can do it at quarter one. And you can say that the average for quarter one, and because we're doing quarter one, we'd actually want to just find the averages for quarter one. So, and the idea is once you do that, you add the value to the trend line and then you get your point either here, or if it's negative, perhaps here. And then that's basically your value for the estimate for quarter one of 2014, which is what it was asking for. So now we need to actually portray this into words. Well, the first thing I said is that we need to plot 4-point moving averages. And now with the average, or with the averages, we plotted all these points and then we drew the trend line. Now the idea of where I extrapolated the data, or I extrapolated the trend line to get to quarter one of 2014, and then the mean seasonal effect that we calculated, or whether it was this value here or this value here, we added to the trend line, and that's basically the rest of the 2 marks. And each of those bullet points there is 1 mark each, and that satisfies our 5-mark requirement. The key pitfall here for most students is to describe that keyword. Most people would see, or they would think, to use otherwise, and they might actually go off on a tangent and start actually trying to do something with this graph. Now obviously I made all this data up and I just drew this trend line completely off the top of my head, so there's no relevance to that. It was just to explain the actual process, to show you the methodology behind the actual process. And describe is actually quite a nice question because you just have to say what you do. Just imagine you were speaking to someone and they asked you, well, how do you do this? And then you just speak to them like a friend and just explain what you're going to actually do. You plot the averages, draw a trend line, calculate the mean for the quarter one, extend the trend line, and then add or subtract to get to your actual value. The incomplete table gives some information about the number of births in the USA, the total population of the USA, and the crude birth rate for the USA in 1960 and 2021. So we need to find the number of births, and we also need to find the crude birth rate for the respective years. Now they're given us the formula. Ironically, I think this is probably the least useful formula they've given to us, and it does come up sometimes, but I just feel like they could have given any other formula, and this is an easy one to remember in some respects. But let's not moan about that, and let's just get started on 1960. This is just a simple plug and go. We know that we need to do 23.7 is equal to the number of births multiplied by 1000 divided by the total population. Now you can go with 179.3, or you can convert it into the actual number, which I'm going to do now. The mark scheme accepts both, however I'm going with the latter because technically it just makes sense to do it per person rather than in millions, but it's just personal preference at that point. Now you can do some rearranging. You can multiply by 179.3 million and then divide it by 1000. I'm just going to do that straight into the calculator, and we get the number of births is equal to 4,200,000. 249,410. Now you can see why it gets a bit harder when you use this 179.3, because you'd have to do 4.249410 million, and you'd have to do rounding, and it's not really good to do rounding for such a large number like that. But I'm not against that. You can do that if you wanted to do that, and it might be easier to spot that. For 2021, we don't know the crude birth rate, so we're trying to actually find it. We just plug the numbers in. We do the number of births times the total, times 1,000, divided by the total population. If you type this into the calculator, you get this value. And we'll round it to 3 significant figures. The table gives information about the crude birth rate for France and for Germany in 2021. As you can see, France had a crude birth rate of 10.9 compared to Germany's 9.6. Jan concludes that the population of France increased more than the population of Germany in 2021. Explain why Jan may not be correct. The first thing is that this is a rate. This isn't a definitive number. So, well, France has a higher rate. Germany could have a bigger country. Therefore, just because France has a higher rate doesn't necessarily mean that they had a higher number. And we're not given this number, so we can't say for sure that she's wrong, but we can't say she's right either, because she could be plainly wrong. So that would be a good reason to put. Another reason you could put is the death rate. Now, it's just saying that the population of France increased, not the number of births increased. Now, the number of births, then you'd be limited to this one. You don't know the actual number of births, you only know the rate. However, since it's saying the population in general, frankly speaking, people die or are given birth to, and hence we don't know the death rate, so more people could be dying in France compared to Germany. Then we can conclude that the population might not increase in France as much as Germany. So you could also put the death rate about that. Question 13. A biased coin is twice as likely to land on heads than tails. An experiment involves flipping 9 identical biased coins. X represents the number of heads obtained in the experiment. Michael says that the values of X can be modeled by the distribution B, N, and 2/3. Write down the name of this distribution model. This is binomial. I can't really explain it much further than that, but when you see a B, that's basically B for binomial. And there's so many different distributions out there, but for GCSE statistics, you only need to know about the binomial and the normal distribution. Part B. Using Michael's model, show why the mean of X is 6. If X is the number of heads, then we can model it binomially, and where N is the number of trials and P is the probability of gaining a head. And this is literally how you write it out, and you see this commonly written in A-level. The mean of X is basically the mean of the binomial model, and the mean of the binomial model is NP. So if we show this, we can just do 9, which is the number of trials, multiplied by 2/3, and you get 6. And guess what? That matches the mean of X. The experiment is carried out 15 times, and the number of heads obtained in each experiment is recorded. Michael uses his model to find an estimate for the number of experiments in which the number of heads recorded is exactly 6. Find Michael's estimate. Okay, so the specification states that for these types of questions, and I'll concede it right here, binomial distribution is probably one of the hardest topics of GCSE statistics. This is the one that is set right at the back of the paper most of the time, and is set aside for those students who want to be aiming for a grade 8 or 9. However, we've kind of drawn the short straw here. According to the specification, when we have to do types of questions like this, I'll explain in a minute, but we do something called Pascal's triangle or choose notation. However, the latter is more commonly done at A level. Now, for the Pascal's triangle, they said that n will never be greater than 10, which is a nice thing, and they never typically go above 6 or 7. However, this question kind of means we have to do the long-winded way, and it makes the choose notation look much more rewarding. Now you can see why I was regretting doing this method. However, this is the method that is typically taught at GCSE, and the choose notation method is not vastly taught at GCSE, and for a reason, because most of the time it makes more sense to do it up till probably about here, and after that we get to the ridiculous coefficients, and this is Pascal's triangle. Now the idea you should have gathered by now is that you add each of them diagonally. So 1 plus 1 gives 2, and here 2 plus 1 gives 3, and let's pick a random one here. Let's say 4 plus 6 gives 10. And you keep doing that, and you basically can go on forever. Now there is a much more nicer way, and it's called choose notation, and it involves factorials and all that whatnot. However, at GCSE you're not really expected to use that method. However, here it makes sense that you would in an A-level exam anyways, but we're going to do it this way, and for 4 marks, you really wouldn't want to be doing this. That's what I meant by drawing the short straw. So the way to approach this question. So he carried out the experiment 15 times, and he needs to find a model, or he needs to find an estimate for the number of heads where it's exactly 6. Now the probability of getting a heads is equal to 2/3. And we need to label this as a success. And Q, let's say, is the probability of failure, or not getting a heads, and that would be 1/3. And this triangle on the right here is called Pascal's triangle. Now I'm going to try my best to explain it as quickly as possible. We have p plus q to the power of n. This is binomial expansion. I recommend you watch a video on binomial expansion because you're going to need it here. This is when n is equal to 0. This is when n equals 1, 2, 3, and so on. And now we're looking for p plus q to the power of n, and what the idea is that when you expand it, these are the coefficients. And I'm not going to explain the actual method here because it'll make more sense in a separate video. The idea is that we need to find the value of n, which is going to be 9. And we know it's 9 because he does it 9 times here. So we're looking for that, or p, which is 2/3 plus that. So p plus q to the power of n, which is 9 because he does it 9 times. And we need to basically expand that. Now that is quite daunting, and I'll admit that is quite daunting for me. Luckily, we found it when n equals 9, we know our coefficients. I'm just going to expand it out for you. If you do not know this, don't even attempt it right now. Go and revise that question. I'm just going to expand it from now. We're interested in this one, the number where p to the 6 is equal to exactly 6 heads. And now we just need to put the value of that in. We can have 84 multiplied by 2/3 to the power of 6 multiplied by 1/3 to the power of 3, which is equal to 1792 divided by 6561, or 0.273. He does this 15 times, and since each has a probability of 0.27, it happens roughly 4 times. Part D. Write down 2 assumptions which Michael needs to make about the experiment so that the distribution of the binomial model is an appropriate one to use. I'm going to quickly write BINS. It stands for binary, independent, number of fixed trials, and same probability. The idea is they are your 4 assumptions, and now you only need to choose 2 of these, so choose any 2 from these 4 letters. And the main thing that you need to do is you need to put it into context. I'll go with the two simplest ones, that the probability of heads remains constant at 2/3, and that there are only two possibilities: you either get a heads or not a heads, i.e. tails. I'll concede that not only is this a difficult question to be doing in the exam, but it's definitely difficult when it's 10 o'clock at night and it's quite a hot day in the UK for once. Anyways, this was paper 2 of the specimen hire.